we want to examine the topic of forces and see how we use angles with the second law. How do angles work with our force and interaction diagrams? And how do we go back and forth between these two representations of the physics? Now, since this is the start of another unit, it's good to take a moment to think about how we've been doing so far in our grade 12 physics course. A little while ago, I asked you to think about your personal goals for the course. So, you might remember that you selected one of these goals here as your goal for the previous unit. And we've just had our unit test on that topic. So you might have a good sense for how you're doing. So now let's think about how you're doing in the achievement of the goal that you set for last time. So take a moment to read this through. Select your letter, face down when you're ready. Okay, ladies and gentlemen, eyes to the front and hold them up. Okay, just hold them up for a moment there as I take a look around. Seeing lots of B's, which is very good. A few A's in there as well, which is excellent. Thank you very much. And so some of you are pointing out some C's and E's and other things. So think very carefully about those aspects of your goals and what you can do to help yourself out during this next unit. Please come and talk to me if you'd like some advice or some hints, we can help you out. So ladies and gentlemen, our task for today is to take a look at forces in two dimensions. You're going to be making use of our dynamics carts. So they live in the cupboard over here. Please, when you return them, return the carts to the cupboard upside down. That way, when somebody opens the cupboard door, there isn't an avalanche of carts as they roll out and attack the person. Okay, so make sure they're returned upside down. You're going to be making use of our spring scales, which can be found in the drawers at the back. When you use spring scales to measure forces, always choose the spring scale that is most appropriate to the measurements you're going to make. So if you're making fairly small measurements, don't grab a 50 Newton spring scale. If you're making very, very large measurements, well, the 5 Newton scale won't do the job at all. So think carefully about your measurement devices and your uncertainties today. And we want to learn how to work with angles and forces. This is your first investigation in your new groups as well. So please remind yourself of the good habits and the responsibilities of our roles. If you have not yet acquainted yourself with the other members in your group, please introduce yourselves. I did my best to try to match up all the requests that people made in the formation of the new groups. So please introduce yourselves, choose your roles for today, adjust your seating, and get started.
This thing I had to do on the place, there were like 4 different quizzes. You unlock it by scoring 100% of the previous one. So I first did the quiz, didn't score 100%, and they're supposed to do their reading. I never did their reading, so you just retook the quiz again and again and again and again. It took me 4. What's the max amount of final corporation? It's $500,000. The max amount of final person get is $25,000.
But they don't tell us.
Does that have tech? Today it's due. So I did yesterday.
Oops, did that wrong.
we're saying 30 degrees up, but we actually assume it's like actually in the upwards direction.
So 30 degrees in the right direction?
Yeah, and then...
in the right direction,
Yeah.
and then 30 degrees up from that.
Yeah. Okay.
Okay.
You have your initial vector, which is you have your delta f, no, your delta v vector, right? And then you draw the two things that, like,
Yeah, but how do you label them?
the ones, I labeled mine two. So you have F2 and then
F2x and F2.
Hey guys. You're working on a prediction there. And what did your group decide for the size of those two forces? Who's our speaker today?
F2
Gabriel.
F1. Because like F2 has like a x and y. If the card's not moving, the x component of F2 should be the same as the F1.
So there's like extra courses for F2.
Because of that y component. Good, good. What do we understand about what's happening to this object? It's at rest. So what does that tell us about the forces acting on it?
It should be equal in opposite directions.
So all the forces should be balanced.
But why F2x is not equal to F2y though?
So that's an important question for what we're learning today. And it goes back to what we learned when we were studying projectile motion about the forces in each perpendicular direction. What did we decide about those forces? So we're going to be seeing that the forces in the x direction work independently from the forces in the y direction.
So I think just like all the forces added up should be opposite to all the forces added up.
We do this and assume F2 is now 5
You're assuming F2 in the x direction.
in the x direction is now 5
No, I think
Just like
they're supposed to be the constant. Because if this was 12 newtons, that would make this like bigger too, right? And then this all total would be bigger, like much bigger than that.
If they're acting independently from this moment, it should be
But then this would be acting independently. You're assuming that the accelerating in that direction.
So let's think carefully about how the forces are behaving in the x direction. So just that part. We understand that the net force in the x direction equals because we observe that the object remains at rest. So if the forces in the x direction are balanced, then one of the horizontal forces, we call it F1, is being balanced by what? And here's where we need to be careful. What part of F2 is balancing F1? The x component of that force is balancing F1.
Okay, so it should be 5. F2 in the x direction should be opposite to F1 in the x direction.
What do we think? Do we agree with that?
Yeah.
Good. You're on the right track.
These two have to be equal to these two because the car's not.
Okay, whatever.
Yeah, I just say script.
It's just gravity.
Yeah.
Hey, what are you saying now?
F of g n, right? Plus f of a y equals to f of g.
Yeah. Oh, sure, yeah.
A is the applied force. For f of a y, what Jonathan and I labeled was this force, the one that is in the one that's like 30 degrees right and 30 degrees upwards.
Hey guys, I have a suggestion for how you draw your force diagrams. So one of our forces, F2, is at an angle, and in your force diagram you've chosen to draw its two components. Just to help our force diagram be more visually clear, we'll always draw the single force vector F2. And then if we want, we can draw the dashed line showing its two components. And then when you look at the diagram, it is more visually intuitive. We can see that, oh yeah, there is a force at a 30-degree angle there. Okay? So we'll draw it just like you see here.
But it would always have to be from the center, I guess, right?
Starting from the center, that's right. Okay? So just make an adjustment to your diagram there. Ladies and gentlemen, let's stop for a moment here to talk about our force diagrams. When we draw our force diagrams that have forces at different angles, we want to be careful to show the force vectors and how to introduce the components to it. So our second force that we're exerting on the cart is at a 30-degree angle. So it looks something like this. We can call that F2. And so always draw the full force vector in your force diagrams like this. And then, if you're doing an analysis, you're often breaking up this force vector into its components. So when you do that, use our usual trick of drawing with dashed lines or a different color the components of that force vector. Now, based on your understanding of this situation, if I have drawn this skillfully, what should we notice about the size of the x component of F2 in my diagram? And I can indicate it like that. So how does that look? Is that fairly close? No, not too bad. So take a look at your own diagrams. And since we understand that the forces in the x direction must be balanced, then we know that this component must balance this force here. Now, an interesting question is what goes on in the vertical direction. That's what you're going to look at next. Please keep going. Good. Now, when you're writing down your force value, here we're just describing the size of this force vector F2. So we won't use the vector arrow over top the force symbol. Okay, because we're not talking about its size and direction. Okay? Hey guys, how's it going? Good, good. What did you figure about the forces in the y direction? Who's
this right now?
at the end of this problem here. What did you figure out about those forces?
The normal force and the force y direction for F2 equal to the force of gravity. So it doesn't because there's no acceleration in y direction.
Now, lots of people would say that the normal force has to be the same size as the force of gravity. So is that true in this situation? No, why not? What's happening that's changing the size of the normal force?
Like the F2 is pushing it up, or because the normal force can adjust to match, so all the positive y forces will match gravity. So if there's a upward force from F2, the normal force will shrink. Those are different ways.
So is the table surface doing the full job of supporting this object? No, because there is
Another upward force.
a component of that force helping it to do that. Very good. Good.
It looks like what we calculated.
Yeah, it's matching your prediction?
Yeah.
Good, good, excellent.
Scales have the forces A and
It's up to us how we want to describe that force. You can think of the spring scale as exerting a pulling force on the cart.
Right, tension.
So you could call it tension. You could call it an applied force as if it's measuring the force of your hand. So there's different ways of thinking about it. Okay?
We're not really sure what it means by sine or cos functions.
So in this expression here, you've written for the net force in the y direction Fg minus Fn. Now for Ft, do we mean the full force vector Ft? What do we mean?
Force of tension.
We mean the y component of Ft. So if you're going to calculate that, you would write Ft times for the y component, correct. Okay, well, there you go. Hello.
Oh, we don't know how to draw the force diagram for this. Like,
Where are we supposed to put the components?
Well, let's start by thinking about our force vectors. So what interactions have you identified?
There's a neural force between the incline, the tension force, FA, and gravity.
So we have 3 important interactions. So how many force vectors will appear on the diagram?
3.
Okay, now which is the easy one?
gravity,
Gravity, which points?
down.
Good, good. So we got that covered. Now let's think about the next one. What about the normal force?
It's perpendicular to
The incline.
Good, good. So we know what direction to draw that. And then what about the third force?
Parallel to the incline.
Good. Okay. So that's the correct setup for the forces. And then you can start to think about how the forces are balancing out and use that to help draw a careful force diagram.
Which one?
Ladies and gentlemen, let's stop for a minute here to talk about part B. So in the next part of our investigation, we're going to be placing our cart on the inclined surface, and the incline is making an angle of theta with respect to the horizontal. And that's the equipment that I have set up at the front over there. Now, we want to think about the forces in this situation and think about how to analyze them. When the object rests on the incline, the important physics that could take place would be parallel to the incline. You might imagine if you let go, it would roll down the incline. And so this is an important hint for us that when we analyze the forces, this direction down the incline is the important direction. So we're making a very critical choice with this kind of problem. We're saying that in this situation, I want to use a tilted coordinate system. One where one of the important directions is the direction that is parallel to the incline. And the other direction will be perpendicular to the incline. So when we start to draw a force diagram for our cart, we want to analyze it using this tilted coordinate system. Now, let's think about our forces. So here's our object. What is this object interacting with at this moment in time? Which objects is it interacting with? The ramp. It's interacting with the ramp, the incline itself. So that's going to be a normal force. What direction is that force going to act in? So hands in the air, fingers in the air. So here's our inclined surface. In what direction will the normal force be? So we understand that normal forces always point perpendicular to the surface. Good, good. So if this is our surface here, the normal force will point like this. What else is this object interacting with? The ramp? With the earth. And there we have a gravitational interaction. What's the direction of that force? Is it any different?
No.
Since the object is on an inclined surface? No. Force pointing down. Are there any other interactions? So you're holding it with a spring scale or with your hand. You can think about it either way. And what direction will that force be?
Parallel.
And you can call it FA, the applied force your hand is exerting on the object. Okay. So this is the picture of the forces acting on the card at this moment in time. And because we are now thinking about it using a tilted coordinate system, when we think of the components for the force of gravity vector, we want our components to be parallel to the inclined surface and perpendicular in the x and in the y directions. So our component triangle now looks like this. So be very careful with your setup when we start using an unusual coordinate system like this. And now, an important challenge for you is to figure out this angle. Please keep going.
It's gonna be 90 minus theta here, and then the whole thing is gonna be a right angle. I don't know how to explain it. Right, and then to get that right angle, you're gonna have to do plus theta.
So this is the kind of reasoning that we want to use.
I don't know how to.
So just make sure you can explain it to yourself and your fellow group members carefully.
But is it theta?
Well, this is what I want you to convince yourselves of.
Okay, but you're gonna tell us that.
Yes.
Yeah, okay.
Ladies and gentlemen, let's talk for a moment about our angles. Now, I've added into our force diagram here the angle that you'll be measuring. So there's an angleometer hooked up to the incline there to be able to use for your measurements. And it'll give you the angle between the incline and the horizontal. And let's take a minute to think about how these angles work out. So if this is angle theta, let's just make up a number. Maybe this is 30 degrees. Then, in this triangle here, what will this angle be? Which equals 60 degrees. So if this is 60 degrees, what angle is this? So if this is 30, how do these two angles compare? So make sure you can go through this process of using your good old grade 9 geometry to convince yourself that you can correctly identify the angle in your component triangle. This will be a fundamental skill for us in grade 12 physics. We're going to be doing a lot of work analyzing forces on an incline. So it's critical that you feel comfortable finding this angle. So if you're not sure, talk about this a bit more with your group. Call me over to help you out. Now, just a quick discussion of the forces here. The forces in the x direction. What force balances the applied force you exert? It's the x component of the force of gravity. And on your force diagram, you can carefully show that. What force balances the normal force? FGY. So we can carefully show that. And if you've drawn it carefully, then the size of those line segments should be the same. So how does the size of FG compare with FN? FG must be bigger. Good, good. Keep going. And what's your prediction?
Like 4.8. Is it 4.6?
Parallel into parallel. Yeah. What is it?
4.8.
So does that agree with your prediction?
Yeah, we got 4.9.
We got 4.9. Oh, yeah.
And what was your uncertainty?
Like, last one is 0.1.
So do they agree?
Yeah, so yeah.
Good, good.
What do you think was gonna? I can't figure out. I don't know how. See how the line is? Does that mean like?
What's your prediction?
I predicted like 20, but it's actually 6.
Okay, so you need to go back and look at your calculations. Okay?
Stop moving.
It's 5.5.
Yeah, I was thinking.
I'm more steady. Okay.
5.5.
Does that agree with your prediction?
Yes, with
Good. So does that agree with your prediction?
I guess the uncertainty, yes.
What is your uncertainty?
20%? No, wait.
Well, your uncertainty is probably 0.1 or 0.2 newtons.
Yeah.
So does that agree with your prediction? So that means that something happened at the calculation stage.
Okay, I was wrong.
Take a very careful look at your trigonometry. Okay? And then quickly recalculate. Okay? You're so close. You're so close.
What do they